to the use of these names, such as elemental enteral feedings, which were designed, for the most part, to find ways to maximize the delivery of nitrogen to the host. As we were talking before, the target, the goal was to maximize nutrient delivery. We know protein is important and is critical, so let's find ways to do that. And that has led to modification of proteins. Today, in enteral feedings, we have several choices. We have intact proteins, we have hydrolyzed proteins, which are peptide-based, and we have amino acid formulations. This has derived into a classification of so-called elementality of diets, amino acids obviously being the more quote-unquote elemental compared to intact proteins, which are the natural way that the proteins occur in most foodstuffs or food ingredients. And the manipulation of proteins to maximize this delivery has led to this development of the so-called enteral feedings. Next slide. If we look at nitrogen delivery, we can very roughly classify, as we said before, enteral feedings, or the type of enteral feedings that we use for our patients, into those that contain intact proteins only, those that are hydrolyzed and contain mostly peptides of varying lengths, or those that are either pure amino acid or have large concentrations of amino acid. Next slide. We won't go into a long discussion of the pros and cons of each one of these forms of protein delivery. Obviously, intact proteins tend to be the natural way they occur in patients with no digestive or absorptive problems. They can be perfectly acceptable and adequate for delivery of nitrogen. And as we said, depending on the type of intact protein, we may have different functionalities from the point of view of both gastric emptying or intestinal transport. There is a general tendency for casein, as we said, bovine casein, to slow gastric emptying or to increase the hardness of stools, while whey has the opposite effect. On the other extreme, on the left, we have the high amino acid or pure amino acid formulations. These, of course, are more readily absorbable from the point of view of the individual amino acids for those small number of amino acids that are absorbed as such, since a large percentage is absorbed as di- and tripeptide. The drawback to those amino acid formulas, of course, is that they do tend to have less support of intestinal mucosal structure, as a number of studies demonstrate. Di- and tripeptides can actually be better absorbed than amino acids alone. But one of the bigger problems is that delivering all nitrogen as amino acid predominant or pure amino acid will increase significantly the osmolality of the formula, and that may, depending on the individual case, lead to increased intolerance from the osmotic point of view. And in the middle, we have what we consider the formulas that have peptides or are based on hydrolysates, which are somewhere in the middle of both extremes. Those have the potential of continuing to be well absorbed, decreasing the chances that you develop intolerance either from intact protein or amino acid proteins, and as we'll talk a little bit further, do help also to support structure and function of the GI tract. Next slide. As we said before, when we meet the goal of enteral nutrition, then we have decided that we want diets that help support the host by providing adequate micro and macronutrients. But what supports the GI tract mostly are those things that we do not absorb. In other words, it is the food in the intestinal lumen that supports gastrointestinal function that we typically tend to forget, particularly when we talk about these elemental diets. Next slide. Enteral feedings, in general, are then going to be a combination of macronutrients, carbohydrates, fats, plus a different type of protein, as we said before. And for the most part, elemental and semi-elemental diets and most polymeric diets concentrate, or their development has concentrated on what is absorbed, in other words, what's going to be useful for the host, and were designed to help decrease the digestive work, or in many cases, which we'll talk about, the so-called digestive residue. So what's missing in most so-called elemental or semi-elemental diets, which are defined by the types of protein and protein hydrolysates or amino acids that we discussed. What's missing is what is not absorbed. And from those of you who have heard me talk about the gastrointestinal tract, what's in the lumen is as important as what is not in the lumen, as important as what gets absorbed. And I think today, in modern nutrition, certainly for the healthy host, there's a general and universal consensus that the so-called residue or roughage or fiber, and these are words that you tend to put in quotes because unfortunately nobody has adequately defined residue or roughage, and we'll talk briefly about that. We do have a definition of fiber, however. But in general, I think most people would accept the fact that fiber is, quote unquote, a good thing in the diet, and most people today would agree it is absolutely necessary for intestinal health. So why is it that we eliminated fiber from the diet of many individuals who have mild or even severe intestinal dysfunction? And it is interesting when we go back historically to try to understand this. There's probably two origins you can hypothesize. Next slide. The first origin, which many people point to, is the fact that because of the space program and because astronauts had to be in space for a long time, and we didn't want to handle too much waste, which was very complicated to do in no-gravity situations, the idea was to figure out if there was a way that astronauts could eat something that would be completely absorbed and therefore not eliminated. And what you see in this picture is one of the first portable waste management systems, which, and I won't tell you how the cup to the left corner was used, but in those capsules, particularly the early Gemini and Mercury projects where astronauts had to be for more than 72 hours orbiting the Earth, some kind of system had to be developed. As you see, that was very complicated. But the other thing that was found out during the space program was that sooner or later you had to eliminate some waste, and even if it wasn't solids, i.e. residue, it was going to be liquid waste. And it was going to be very hard not to figure out a system to do this. So that was one of the first origins of the so-called elemental diets with the so-called zero residue, if possible, which led to the development of some of the potential peptide and amino acid formulations with absolutely no intestinal fiber to see if you could absorb 100%. But we know that that doesn't happen. We know people eliminate whatever they need to eliminate and that the gut still secretes even if you don't eat anything. Next slide. Fortunately, the space program has figured out very elegant ways of doing it, and what you see on the right side is the current toilet of the Atlantis space shuttle, which is a very fancy machine which has allowed astronauts now to eat not only a regular diet, but a diet with the right amount of fiber and the right amount of fluid that allows them to support themselves for long periods of time in space.